So today, we're going to look at the fractional quantum Hall effect. And we are going to focus on two amazing aspects of the fractional quantum Hall effect. The first is the realization that the fractional quantum Hall effect comes with excitations, quasi-particles that carry a fraction of the electron charge. The second is that if you put a system of a fractional quantum Hall state on a torus, and we'll talk about what that means, but you put it on a torus, you find that the ground state, which is gapped from the rest of the spectrum, there are no gapless edge states on a torus, the ground state will have a degeneracy. And that degeneracy will be topological, will not depend on any symmetry of the problem. But to start with, let's look again at the quantum Hall plot. And we know that there are states, there are plateaus like this one and this one, in which sigma xy is e squared over h times nu, and nu is a fraction. Examples are 1/3, 2/5, and others. And we are going to focus on 1/3, which is the one that's most prominently observed in experiments. We will deal with the more complicated fractions at a later stage of this course. So we are after the fractionally charged quasiparticles. Our main tool in our search for fractionally charged quasiparticles is going to be this system of a disk where the electrons are subjected to a perpendicular magnetic field and form a fractional quantum Hall state with nu equals 1/3. And on top of the disk, there's also a flux threading the hole inside the disk, and that flux is going to be a major tool for us. We are going to change that flux in time, starting from a value of 0 and ending at a final value, which eventually we're going to choose to be the flux quantum phi naught, which is hc over E. We will elaborate on the meaning of that value of the flux later on. Now, let's look at this experiment from a classical and a quantum mechanical standpoint. So classically, classical physics knows only about forces. So when we change the flux as a function of time, we generate an electromotive force which is azimuthal. We generate an azimuthal electric field which is -1 over 2 pi RC times the derivative of the flux with respect to time. Of course, if you are inside the solenoid, you also feel a Lorentz force, but we are not. We are thinking about what happens in the disk. Now, the electrons in the disk are in a quantum Hall state, and therefore there will be a radial current that's going to be formed out of that electric field. And the value of the radial current is going to be sigma xy times the electric field, the azimuthal electric field, which would be -1 over 2 pi RC E squared over h times nu times d phi dt. That's the radial current. Now, out of that radial current, there will be a depletion of the charge here and an accumulation of the charge here. And we can calculate how much charge goes out of the inner edge and into the outer edge. We can calculate that because we know that the time derivative of that charge plus the integral along a curve. Let's look at a curve that's a circle, a distance r from the origin. So an integral along that curve of dn dotted into j, this is 0, which is another way of saying any charge that goes out of here will cross the circle that we are thinking of. Now, this integral, the integral along a circle would cancel this factor of 1 over 2 pi r, and this integral will come out q dot equal e squared over h times nu divided by c, d phi over dt. Now, that allows us to calculate not only the time derivative of the charge, but how much charge actually accumulates throughout the entire process. We will do that by integrating both sides over time, and that will tell us that Q is going to be E squared over hc times nu times the final value of the flux. We just integrated d phi dt over time. Now, this is what classical physics tells us. It tells us how much charge accumulates at the outer edge or depletes from the inner edge. Now, let us see what quantum mechanics has to add to this story. So, quantum mechanically, the electronic system, despite not feeling any Lorentz force out of the magnetic field in the solenoid, the spectrum of the electronic system depends on phi. This is the essence of the Aharonov-Bohm effect. The energy as a function of phi, the spectrum depends on phi. Now, the dependence is not arbitrary. Due to the Aharonov-Bohm effect, the dependence on phi is periodic with a period of one flux quantum. So the spectrum here at 0 and the spectrum at one flux quantum is going to be the same spectrum. Now, we're going to evolve the flux in time slowly, adiabatically. The quantum mechanical adiabatic theorem tells us that if we change this parameter, the flux, slowly in time, and the system starts in an eigenstate, it will stay in an eigenstate all throughout the evolution. Therefore, if it started in the ground state, and we time evolve the flux to a value of one flux quantum, it will end up in an eigenstate. But since the spectrum is periodic with a period of one flux quantum, the final eigenstate will be also an eigenstate of the original system. So the system evolves from one eigenstate to another. Those two eigenstates are not the same because charge moved from the inside to the outside. How much charge moved? Let's see. Q for one flux quantum is going to be E squared over hc times nu times one flux quantum here, namely times hc over E, which is nothing but E times nu, which is the charge, the fractional charge of the Laughlin quasiparticle, E times nu. So what did we see? We saw that as we evolved the system in time as a function of flux, we pushed out 1/3 of a charge from here to here, and the system ended up in an eigenstate. In an eigenstate of the final value of the flux, which is also an eigenstate of the initial value of the flux. So the system has eigenstates that carry a fractional charge on each of the two edges. Now, those are eigenstates, which mean that they live forever. They will stay the same for at arbitrarily long times. Now, let me draw again this axis to tell you one more thing about it. So there is, I have to admit, an aspect which this analysis hides under the rug. And this is that if our ground state evolved to some state that has a 1/3 charge on the outside and minus 1/3 of the inside, there must be another state which presumably started from minus 1/3 plus 1/3 that evolves to become the ground state. So there must be another state that does this evolution. Naively, you would expect that in such a situation, there would be an avoided crossing here, and that if you do your process adiabatically enough, you would go from the ground state to the ground state, avoiding the plus 1/3 minus 1/3. But now that we understand the physics of this excitation, we understand that we are taking out 1/3 of a charge and leaving behind minus 1/3 of a charge, we also understand that this avoided crossing is the process of a tunneling of a 1/3 charge from the outside to the inside. Now, that is a tunneling process. If this distance is macroscopic, the amplitude for this tunneling process would be exponentially small. What we are thinking implicitly of here is a situation where the size of the system is in the thermodynamic limit, and therefore this amplitude is vanishingly small. Alternatively, we change the flux adiabatically, but not infinitely adiabatically. We change it in such a way that we do not see this avoided crossing. So this is the fractionally charged quasiparticles. Now, this is a kind of revolutionary concept. We have a system where all charge carriers have the same charge, yet there is an excitation that has a fraction of that charge. That concept has many consequences, but some consequences it does not have. You cannot take 1/3, you cannot take this 1/3 of a charge and take it out and move with it to the other room. That's not going to work. It lives and dies on the two-dimensional electron gas where there is a fractional quantum Hall state. But it does have many consequences. Some you will see in the experimental segments of this course. And some you will see now when we talk about the ground state degeneracy on a torus. So we discussed the physics of a single disk, and we saw that we can generate quasiparticles with a fractional charge by inserting fluxes through the holes of the disk. Now what we're going to do is to look at two disks and generate out of two disks a torus. And the way we will do that would be taking one disk with electrons at filling factor 1/3, and another disk with holes at filling factor -1/3. So in terms of the edge structure, this disk would have maybe an edge this way, and the other one would have an edge this way, and the other disk would have edges moving in the opposite direction. Now we are going to couple those two disks in such a way that will generate a torus. Now, what do we mean by a torus? So first, how are we going to do that? We're going to stitch, and I'll explain exactly how, these two edges to one another and the internal edges to one another. That would generate a torus, like the tire in your car or in your bike. And as you can see, this structure will have no edges of its own. So the torus will be a geometry that has no edges of its own, and therefore the entire thing we will look at will be the bulk. Now, what do we mean when we say we couple these two edges to one another? So we have two edges moving in opposite directions, and we're going to allow electrons to tunnel from one edge to the other. Of course, quasiparticles cannot tunnel from one edge to the other this way, because that would involve going through the vacuum. And fractional charges cannot exist in the vacuum. Quasiparticles can, however, tunnel this way within the 2D system that's entirely a fractional quantum Hall system. And we are going to take this size to be very large to make that not happen. So if we look now, if we decouple the two disks for a few minutes to discuss the physics of each one of them, then you see each disk has two edges, and they have this edge has a certain charge, this one has a certain charge, and so about the other two. So we have 4 charges in the 4 edges, which we are going to call Qi, Q1, Q2, Q3, Q4. And those charges are combined of an integer part and a fractional part. So there will be an integer part of charges n. There would be n1, n2, n3, and 4, plus a fractional part f1, f2, f3, f4. And now we're going to analyze what happens to each and every one of them. So first, since each disk can have, on the whole, must have an integer number of charges, the fractional part here and the fractional part here should cancel one another. So F1 plus F2 must be 0, and F3 plus F4 must be 0. This is a must. This is not negotiable because fractional charges cannot exist outside of a 2-deg fractional quantum Hall state. Now, next step is thinking about the fractional charges of 1 and 3, how they constrain one another. Now, this constraint is not part of the fundamental requirement of the total charge on a disk being an integer number, but it is a constraint that comes out of of our interest in analyzing what happens in the ground state. So in the ground state, the total charge here, the total charge of this edge plus this edge should compensate one another, or should be equal to some background charge, which is integer. So the sum of these two charges should be an integer, meaning that F1 plus F3 should be 0, and F2 plus F4 should be 0. Looking at these four requirements, two out of fundamental requirement on each of the two disks, and two out of the desire to look at the ground state, looking at these four requirements, we see that F1 determines F2, F1 determines also F3, and F3 determines F4, and F2 determines F4. Altogether, we have only 1 degree of freedom in coming out of these four equations. And once we fix F1, we fix all the others, and F1 can be either 0, 1/3, or 2/3. So our analysis of the fractional part of the charge results in the observation that the fractional part of parts of all edges are coupled to one another, and we have only 1 degree of freedom to choose. So there will be states with 0 fractional charge on all edges, states with 1/3, and states with 2/3. And what we will now see is that energetically, all those states will have the same energy. And therefore, that will be the source of the ground state degeneracy. So to look at the energy of those three states with 0, 1/3, and 2/3 fractional charges, we need to analyze what happens to the integer part of the charge. And for that, let's look a little bit closely at the tunnel coupling between the two edges. So we are now going to let integer electrons jump from edge 1 to edge 3 and from edge 2 to edge 4. Now, we can draw an analogy, or we can get some inspiration by reminding ourselves of the physics of a Josephson junction. So in a Josephson junction, we have two superconductors. Let me call them A and B. Each one of them has a certain number, integer number of Cooper pairs, Na and Nb. We let Cooper pairs tunnel between A and B back and forth, and therefore Na minus Nb, so the difference between the number of Cooper pairs because of the tunneling becomes undefined. Becomes with a large quantum uncertainty. And in fact, the quantity that is well defined is the conjugate to this variable, to Na minus Nb, and this is the phase difference, phi, which is defined. And we know that the energy of a Josephson junction becomes proportional to minus cosine phi, and has a minimum at some value of the phase difference between the two superconductors, where the difference between the number of Cooper pairs fluctuates wildly. Now, as to the sum of the two numbers, the number of Cooper pairs here plus here, that one doesn't change when you tunnel one from here to here. And in fact, is well defined. So NA plus NB is well defined, and it's minimized by whatever constraints are imposed by charge neutrality of the junction. So something quite similar happens in our problem. Let's look at those two edges. Similar story will happen in the other two. Those two edges, we have two integer number of charges, n1 and n3. Now we introduce tunneling. And this tunneling is what will stitch the two edges to one another. So now n1 plus n3 is not affected by the tunneling, and it stays constant and well defined. But n1 minus n3 fluctuates because of the tunneling. Every tunneling electron changes this number. So n1 minus n3 fluctuates and is very undefined. Now, if I look at the probability distribution function for this particular variable, n1 minus n3, and I ask myself, how is the distribution function distributed over possible values of n1 minus n3? It's very broadly distributed. The uncertainty, the fluctuations in n1 minus n3 are very, very large. Ideally, they would go as high as infinity in the thermodynamic limit and so on and so forth. But they are very, very large. Now we come with three values of the fractional part, 0, 1/3, and 2/3. And we ask, how would the energy of this entire system be affected by this probability distribution, by the average of this probability distribution function changing by 1/3 in one direction or the other? And the answer is the change would be very, very small, would go to 0 in the thermodynamic limit, because this width of the distribution function is thermodynamically large, therefore approaches infinity in the thermodynamic limit, and way, way larger than the 0, 1/3, minus 1/3 charge that separates between the three states. Therefore, the energies of those three states would not depend on what is the fractional part of the charges on each of the edges, and there would be a degeneracy of the ground state, a threefold degeneracy of the ground state, once we put the entire thing on a torus. Now, you see that this degeneracy comes hand in hand with the existence of a fractional charge. And indeed, that is the rule of the game. That is going to happen always. That once you have a fractional charge, there will be a ground state degeneracy on a torus. There's another aspect to this fractionalization, and this is the fact that those fractionalized quasiparticles also satisfy fractional quantum statistics. That is very interesting, but does not belong to our segment today. So what we saw today are two important and unique features of the fractional quantum Hall effect. The existence of quasiparticles whose charge is a fraction of the electron charge, and the existence of a degeneracy of the ground state when a fractional quantum Hall system is positioned on a torus. Those two came out of very simple-minded analysis. We will find them also in a more elaborate formalism in later segments of the course.